Imagine a massive bridge, stretching across a huge canyon. Or maybe something really delicate, like a medical implant that's literally saving someone's life. What's the invisible thread holding these critical things together?
It has to be the precision, right?
Yeah.
The absolute precision of every single weld.
Exactly, because even a tiny, unseen flaw, well, it could lead to catastrophe, structural collapse, device malfunction, you name it.
Absolutely. In welding, good enough just doesn't cut it. The stakes are way too high. It all boils down to making sure everything is exactly as it should be.
And that's why today we're taking a deep dive into this surprisingly complex world of calibration and validation for arc welding equipment. It's not just about, tweaking a dial and hoping for the best.
Not at all. It's about meticulous accuracy.
Yeah.
We're talking about a process where like a millimeter of wire or just a single volt can literally determine if something holds together or fails.
So our mission today, let's pull back the curtain on the key standards that guide this precision. We need to really unpack the differences between calibration and validation.
Yeah, and explore why some of these welding measurements are, frankly, notoriously tricky to get right.
And ultimately, reveal what it truly takes to guarantee that welding equipment performs exactly as it should every single time.
You'll find that the smallest details here can have the biggest impact.
Yeah.
Not just on the weld, but on the safety and reliability of everything from huge oil rigs right down to tiny pacemakers.
Okay, so let's unpack this. When we talk about ensuring accuracy in welding equipment, where do we even start? Is there like a foundational standard?
There is, yeah. Our sort of guiding light here is a standard called BSEN 50504.
BSEN 50504.
Think of it as the code of practice. It gives clear guidance, both for the equipment manufacturers on the accuracy their meters need, the ones showing current or voltage,
Yep.
and for the end users, making sure those meters give reliable readings.
Right, so it sets a benchmark. And within that standard, is all welding equipment treated the same, or are there different, categories?
Good question. No, it's actually split into two grades, standard and precision. If you're doing manual welding, or maybe semi-automatic, then standard grade equipment is usually what you'll be looking at. It's generally sufficient.
Okay, I think I see where this is going. For the more advanced stuff, like mechanized or automatic welding, that's where precision grade comes in, right?
Exactly.
And what's the main difference there in terms of the equipment needs?
Well, precision grade is essential for those applications. The key distinction is they demand much greater precision for all the welding variables. And often the equipment runs for longer periods too, higher duty cycles we call it, meaning it's operating for a bigger chunk of time without a break.
Gotcha. Now, terminology, this is where I think it gets really important to be clear. Let's start with calibration. How does the standard define that?
Okay, so calibration is defined as the operations for determining the magnitude of errors in a measuring instrument. And usually it involves actually adjusting the readings to minimize that error.
Adjusting, okay.
But here's the really crucial point. Only equipment that has actual adjustable output meters, those physical gauges you can see, can truly be calibrated.
Ah, okay. So if my welding machine just has a dial, maybe numbers painted on, but no actual meter I can tweak, I can't calibrate it in that strict sense, what do I do then?
You've nailed the core difference right there.
Yeah.
That's where validation comes in.
Validation, right.
Validation is defined as operations to demonstrate that an item of welding equipment, or even a whole system, conforms to its operating specification. And the key insight here is that equipment with or without meters can be validated.
Okay, let me see if I've got this straight. So all welding equipment can be validated. You can check if it's doing what it's supposed to do within its limits.
Right.
But only the gear with adjustable meters can be calibrated. That feels like a really fundamental difference in how you approach quality control.
It absolutely is. Understand that distinction. It sort of underpins the whole approach to ensuring quality and consistency in every single weld.
Right. Which brings us to the big why. Why do these processes matter so much? And, when should we be doing them? How often?
Well, they matter because they're just fundamental to solid welding process control. They ensure the final weld consistently meets all the specified requirements.
Yeah.
Without accurate, validated equipment, you're essentially welding blind. You risk costly rework or worse, failures down the line.
Makes sense. So frequency, how often should this equipment get checked? Are we talking daily, weekly, yearly?
BSENOP 504 gives recommendations. For standard grade gear, it's typically yearly, but that's only after an initial consistency check every 3 months for the first year.
Okay, yearly after the first pit.
And for precision grade?
For precision grade, which remember is for those more demanding jobs, it's recommended every 6 months, more frequent.
And what if something changes? Like if the machine gets repaired, do those timelines shift? Oh, absolutely. They can. You might need more frequent checks based on what the manufacturer says, or maybe your own specific user requirements. And critically, yes, if the equipment has had any repair, recalibration should always happen after that.
Right.
And of course, if you just suspect something's off, if its performance seems to have deteriorated.
It stands to reason that the tools you use to check your welding equipment need to be even more precise, right? What are the requirements for these calibration instruments? Can I just, grab any old multimeter off the shelf?
Definitely not.
Yeah.
No, these instruments, they have to be calibrated themselves by a recognized calibrator. And they need to use standards that are traceable back to a national standard.
Traceable. Okay, like a chain of accuracy.
Exactly. It creates this unbroken chain, giving you confidence in the measurements. And yes, their accuracy is paramount. They should be at least 2 times, and ideally 5 times more accurate than the equipment they're actually checking.
Wow, 5 times preferably.
And for that precision grade welding equipment we talked about, you need instruments with even greater precision still.
Okay, let's dive into the nuts and bolts of the actual measurements, because I hear some of these parameters have some real quirks that can trip you up.
Correct.
First up, welding current.
Right, welding current measured with an ammeter. Often it's paired with something called a shunt.
A shunt.
Yeah, basically a very low resistance path that lets most of the current flow past the meter, but the meter measures a small proportional amount, allows for sensitivity. The interesting thing here, the key insight, is that you can measure welding current pretty much anywhere in the circuit. The value should, in theory, be the same all the way around.
Oh, interesting. So it doesn't matter where you clamp on.
For current, generally no. And for AC current, you can even use a tom tester, one of those clamp-on devices. Super convenient, as you don't need to actually break into the circuit.
Okay. Now this next one, arc voltage. This is the one I've heard is particularly fascinating. It's the potential difference right across the arc itself.
Yes.
You'd think the voltage meter on the power source would just tell you that, right? But I hear that's often not the case. Why is that?
You're right, that's a really common misconception. The power source meter reading often does differ from the true arc voltage.
Why?
The main reason is voltage drop. It happens in the welding cables and all the connections because of electrical resistance.
Ah, resistance in the cables? Like friction for electricity?
Sort of, yeah. Just like water pressure drops in a long hose, electrical voltage drops as it travels through cables, especially long ones or ones that aren't thick enough. This means the meter back at the power source will tend to read a bit higher than the actual voltage right there at the arc.
Okay, that makes sense. So the location where you measure is critical then?
Absolutely critical. Ideally, you want to measure as close as practical to the arc itself. Points 4 and 5 if you're looking at a typical circuit diagram.
So let's think practically. If I'm a welder, right, and my machine's meter says, 24 volts, but the true voltage at the arc is actually lower, maybe 22 volts. What's the real world impact? How would I even know? And why should I care?
That's a hugely important point. If you think you're welding at the correct voltage, but the actual arc voltage is lower because of these drops, you could be putting significantly less heat into the weld than the procedure calls for.
Less heat? So weaker welds?
Potentially, yes. The weld might even look okay on the surface, but it could be fundamentally weaker. Maybe lack of fusion or insufficient penetration. It compromises the integrity, and you might not know until it's way too late.
Wow. Okay. So how do you know? How do you measure it properly?
You need external calibrated instruments like a voltmeter connected as close to the arc as possible. Now, practically speaking, for MMA welding, manual metal arc, you can usually get relatively close, maybe within a couple of meters of the arc. But for processes like MIG-MAG, the nearest practical connection points are often a bit further out, maybe at the wire feeder. And even small things like switching from an air-cooled torch to a heavier water-cooled one can actually affect the measured voltage because of the different cable setup.
That's a really subtle but crucial detail.
Yeah.
So minimizing that voltage drop becomes really important for reliable welding. How do we do that?
Right. To minimize these drops, which depend on cable diameter, length, even temperature, the standard advises using current return cables, your earth cables, that are as short, heavy, and low resistance as you can manage. Also, make sure your connectors, both current and return, are suitably rated for the current and that they're firmly attached. Loose or underrated connectors cause high resistance and can overheat.
Got it. Short, thick cables, good connections. What about wire feed speed? Is that something we always need to calibrate?
Not always, especially for constant voltage processes like MIG-MAG, because there the arc length kind of self-regulates and the wire feed speed is inherently linked to the current setting.
So they adjust together.
Largely, yes. But if you do need to calibrate it, maybe for a specific procedure or for a constant current process, the recommendation is quite hands-on, actually.
Oh, yeah.
You measure the time it takes using a stopwatch or an electronic timer for about, say, 1 meter of wire to feed out. Then you carefully measure the actual length of that wire using a steel rule accurately, maybe to within a millimeter. Then you just calculate the speed, length divided by time.
Simple enough, just needs care. Okay. And for automated systems, robots, manipulators, travel speed must be critical there.
Oh, absolutely. Travel speed is crucial for things like welding manipulators, robots, linear carriages, that sort of thing. It directly impacts the heat input into the weld.
Which affects the properties of the weld metal.
Exactly. Its mechanical properties, the microstructure. For standard devices, you can check it simply with a stopwatch and a measuring rule over a set distance. More sophisticated equipment might use something called a tacho generator.
A tacho generator.
Yeah, it's a little device that converts rotational speed, maybe from a drive wheel, into an electrical signal, giving you a direct speed reading.
Clever. And finally, shielding gas flow rate. Is that complex?
No, that one's usually more straightforward. You set it with the gas regulator on the cylinder, and then you check it right at the torch nozzle using a portable flow meter. Relatively simple compared to arc voltage.
Okay, so we've covered the electrical and mechanical stuff. Let's shift gears slightly and talk about temperature in welding. That has its own set of definitions and, I imagine, measurement challenges too.
It does. There are 3 key temperatures we usually define in welding procedures. First is preheat temperature.
Preheat, that's before you start welding.
Exactly. It's the temperature of the workpiece, right in the weld zone, immediately before you do any welding, even tack welds. And it's usually specified as a minimum temperature you need to reach.
Okay, minimum before you start. What else?
Then there's interpass temperature. This applies when you're doing multiple weld runs, building up the weld. It's the temperature in the weld area, including the weld metal just deposited and the nearby parent metal, measured immediately before you apply the next weld run. And this one is usually specified as a maximum.
Maximum between passes. Got it. Why a maximum?
To control the cooling rate and the resulting microstructure, prevent overheating, which can degrade properties. And finally, there's preheat maintenance temperature.
Maintenance?
Yeah, it's the minimum temperature you need to keep the weld zone at. If for some reason welding gets interrupted, you don't want it to cool down too much before you restart.
Okay, 3 key temps. Preheat minimum, interpass maximum, maintenance minimum. So where exactly do you measure these? Does it matter?
Oh, it definitely matters. BSEN ISO 139 gives specific guidance. For material thickness up to 50 millimeters, you measure on the surface facing the welder at a distance of about 4 times the thickness away from the joint, but no more than 50 mil away.
4 times thickness, max 50 mil on the welder side.
Okay. What if it's thicker than 50 mil?
If it's thicker than 50 millimeters, you measure at least 75 millimeters away from the joint. And ideally, you measure on the face opposite to where the heating is being applied to get a better sense of the through thickness temperature.
Right. And how long do you wait after heating before you take a measurement? Can you just slap the thermometer on straight away?
No, that's another critical point. You need to allow time for the heat to soak through, for the temperature to equalize. The rule of thumb is to allow about 2 minutes for every 25 millimeters of parent metal thickness before taking a reading.
2 minutes per 25 mil. Okay, patience is needed.
Definitely. And for interpass temperature specifically, you should measure right on the weld metal itself or on the parent metal immediately next to it.
Makes sense. Now, how do you actually measure these? I've seen those, like temperature-sensitive crayons and paints, even little pills sometimes. They seem handy.
They are handy. Cheap, convenient, easy to use.
But I sense a but coming. But, and this is another one of those surprising distinctions, they don't actually measure the temperature.
They don't. What do they do then?
They only indicate that a specific temperature threshold has been reached or exceeded. So a 150 degrees C crayon mark will melt when the surface reaches 150 degrees C. It tells you it got to at least 150, but it doesn't tell you if it's 150, 170, or 200.
Ah, so they're more like a gonna-go gauge for temperature.
Exactly. More like a check engine light than a precise thermometer. They confirm you've reached the minimum preheat, for example, but they can't tell you the actual peak temperature or the interpass temperature accurately if it's above their rating.
That is a huge insight. So if you need the actual number.
For actual precise temperature measurement, you need different tools. A contact thermometer gives you a direct reading, or for better accuracy and wider ranges, you typically use a thermocouple.
Thermocouple, how does that work?
It works by detecting the tiny voltage generated at the junction of two different types of metal wire, which changes predictably with temperature. They're very common, quite accurate, cover a wide range, but they do need calibrating.
Okay.
Any other options?
Thermistors are also used. These are like resistors whose resistance changes significantly and predictably with temperature. They offer high sensitivity, measure actual temperature, also need calibration, but they're generally limited to maybe around 320 degrees C or so.
Right. And what about really high temperatures or measuring from a distance?
For contactless measurements, maybe for safety or just very high temps, you'd look at optical or electrical devices. Things like infrared radiation thermometers or optical pyrometers. They measure the radiant energy coming off the hot object. More complex, but very useful in certain situations.
Wow, okay, so you've got this whole toolbox of temperature tools, from simple crayons, which aren't really measuring, to complex pyrometers. And understanding what each one actually tells you is key.
Absolutely. Using the right tool for the job and knowing its limitations. Speaking of toolboxes, let's talk about something called the Portable Arc Monitor System, or PMS. That sounds like it might be an all-in-one kind of solution.
A PMS unit is indeed a very sophisticated piece of kit. Its main purpose is twofold. One, to calibrate and validate welding equipment, like we've been discussing. But two, and this is really powerful, it can measure and record all the key welding parameters during the actual welding process itself, real-time monitoring.
Okay, so it does the checks beforehand and watches while you weld. What does it measure?
Pretty much everything important. It usually measures welding current, often using the Hall effect. That's a way to sense the magnetic field around the cable, so no direct electrical contact needed. It measures arc voltage using dedicated connection leads placed correctly.
Like we discussed, close to the arc.
Exactly. It measures temperature, usually with a thermocouple input, wire feed speed, often with a little tachometer wheel that runs on the wire, and even gas flow rate, perhaps using a sensor based on a heating element.
So it's a comprehensive data logger and checker, all in one box.
Pretty much, yeah. A really powerful tool for process control and diagnostics.
It sounds incredibly thorough. So, with all this focus on rigorous calibration and validation, are there ever situations where it's actually not required? Where you can skip it?
Yes, there are some specific scenarios outlined in the standards where it might not be mandatory.
Like what?
Well, for instance, if process verification just isn't required for that particular job or contract, or maybe for small production runs like one-offs or a very small batch.
Okay, for small batches, under what conditions?
It might not be needed if the welding procedures you're using were originally qualified or approved through testing. And crucially, the production welding is done using the exact same welding machine that was used during that initial qualification testing.
Ah, the same machine condition. Got it. What about mass production? Seems like you definitely need it there.
Not necessarily required there either, but again, only if certain conditions are met. The production needs to be controlled by pre-production testing, followed by regular sampling during the run. You need a proper statistical quality control system in place. The process needs to be demonstrably stable between those samples. And the pre-production tests and the sampling have to be done separately for each individual production line or robotic cell.
So basically, if you have other really robust quality control methods that inherently verify the process is staying consistent, then dedicated calibration or validation might not be a separate, standalone requirement.
That's the gist of it, yes. The other systems are effectively confirming the equipment is performing correctly.
Right. Let's talk accuracy levels then. We've mentioned standard and precision grades. What kind of tolerances are we actually aiming for? Does BS 7570 or BSEN ISO 17662 specify numbers?
They do. For what they call grade 1, which is sort of general purpose equipment, the rule of thumb is generally plus or minus 10% for all parameters.
Plus minus 10% for standard.
But for grade 2, which applies to automatic or automated equipment, our precision grade, effectively, the requirements get much tighter. Welding current should be within plus or minus 2.5%.
Wow, 2.5%.
Yeah. And other parameters, generally within plus or minus 5%.
Okay.
Looking more specifically, typical tolerances you might see required are welding current plus minus 2.5%, arc voltage plus minus 5%, Wire feed speed, plus minus 2.5%. Gas flow rate is usually a bit looser, maybe plus minus 20%.
20% for gas. Seems high.
Well, flow measurement can be tricky, and often a bit more variation is acceptable there, maybe plus minus 25% for backing gas. And temperature, if measured with a thermocouple, typically needs to be within plus minus 5%.
It's really clear that the level of precision needed absolutely scales with the complexity and criticality of the job. Let's try to picture this with some real-world examples. Say, just elementary MMA welding, stick welding. What would you typically monitor there?
In practice, yeah, for very basic MMA welding, maybe a simple repair on non-critical stuff, you might only need to monitor the welding current, perhaps just checking it periodically with a calibrated tongue test ammeter. That might be sufficient.
Okay, simple job, simple checks. But now let's flip to the other extreme. High-integrity MMA. You're welding something critical, like components for, I don't know, an aircraft or a nuclear pressure vessel. Totally different ballgame, right?
No, completely different ballgame. In theory, for a high-integrity MMA job like that, you might need to monitor everything. Current, voltage, the rate of lay, how fast the electrode is consumed, or the weld progresses preheat and interpass temperatures, maybe even things like electrode conditioning, how they're stored and handled.
Because any deviation could be catastrophic.
Precisely. Imagine a critical pipeline weld needing to withstand extreme pressures. Any slip-up in those parameters could lead to failure. So to monitor all that, you'd need a whole suite of calibrated instruments. Ammeter, voltmeter, stopwatch, tape measure, thermometer, maybe a calculator. And all of them, plus any meters on the power source itself, would need to be calibrated.
Or you use a PMS unit.
Or you use a PMS unit, exactly, to capture and verify all that data much more efficiently.
Okay. And one more. What about something like MIG-MAG welding, but done by a robot? You're looking for absolute consistency there, weld after weld, right?
Yes, absolutely. Consistency and repeatability are key. So in theory, you'd want to monitor wire feed speed, amperage, voltage, travel speed, gas flow rate, and you'd also be interested in the repeatability of the robot's control system itself.
Making sure setting 5 today is the same as setting 5 tomorrow.
Exactly. Think about automotive chassis welding. Thousands of identical welds, all needing to meet stringent safety standards. Any inconsistency is a major problem. So in practice, for that kind of application, you'd ideally use a data logger integrated with the robot controller to monitor all those parameters continuously. And a PMS unit would be invaluable for initially verifying and periodically checking the accuracy and repeatability of the control knobs or digital settings.
So wrapping this all up, what's the core takeaway? What's the main thing listeners should really grasp from this deep dive into calibration and validation?
I think the most critical point to remember is this. A welding power source can only be truly calibrated if it has meters fitted to it that can actually be adjusted.
Right. The adjustable gauges.
If it doesn't have those, it can only be validated, meaning you confirm that its control knobs or settings provide consistent, repeatable results within its specification. But ultimately, whether it's calibrated or validated, the main goal is the same: to achieve robust in-process monitoring, to make sure that the welding requirements are continuously met during production, ensuring the quality and integrity of every weld.
What a journey. We've really navigated the intricate details of welding equipment accuracy, from those essential definitions, calibration versus validation, which are surprisingly distinct,
They really are.
to understanding why measuring arc voltage is such a unique challenge with those cable drops.
It's a hidden voltage loss, yeah.
And even uncovering the, frankly, surprising limitations of common tools like temperature crayons. It really highlights how much precision is needed.
And we've seen how the requirements scale up, haven't we? From just a basic check with a tongue tester for simple jobs, right up to needing a full PMS unit for critical robotic welding. It's a real testament to how crucial accuracy is in the physical world of engineering.
So what does this all mean for you listening?
Well, it means that behind every single robust weld, whether it's holding up that skyscraper we imagined or securing a tiny component inside a medical device, there's this incredibly meticulous process, a process of checking, validating, fine-tuning the equipment to make absolutely sure it performs exactly as specified, time after time. Hopefully, this deep dive gives you a new appreciation for all that hidden precision that goes into building, well, pretty much everything around us.
It really is a field where those unseen details can have absolutely profound consequences. Definitely. And thinking about all this, if such precise calibration and validation are so critical for these physical joining processes, it makes you wonder, doesn't it, what might be the equivalent calibration standards we need for the information we consume, for the decisions we make in our own lives? How do we ensure our own inputs are truly accurate and our outputs, our actions, our judgments are reliable?
That's a deep thought to end on.
Yeah.
Calibrating our own inputs.
Something to ponder anyway.